Welcome students. Today we're going to begin the Unit 1 notes that are posted on Shobi that contains Chapter 3. We're going to try to do the first 14 slides together, and then I'd like for you to try the homework. A lot of this should be review from your summer assignment. The first thing we want to talk about is the unit in chemistry called the mole. This is the most central, most important unit that we use in chemistry. We use it all year. It's a unit of measurement established for use in counting atoms. So instead of counting atoms one at a time because they are so microscopic, we count them in groupings. The same way we do eggs or donuts, counting those by the dozen, we count atoms in chemistry using the unit the mole. So what is the mole? Well, chemists have developed this value using the number equal to the number of carbon atoms, a very important element in chemistry, in exactly 12 grams of pure carbon. Periodic chart, you'll notice that carbon's atomic mass is 12, and so 12 grams in 12, that's 1 mole. And so the definition of a mole is based on the atom carbon, and everything else is relatively larger or smaller based on its mass. We use techniques such as mass spectrometry to determine the number of atoms that actually make up a mole to be the following. Now, this number is called Avogadro's number, and thanks to this number, we know that 1 mole of something, of any group of atoms, exists of 6.022 times 10 to the 23 units of that substance. So a mole is a lot of something, a lot of atoms, any particular type of atom. You don't have this slide, but that's okay. I just wanted to point out to you that on any given periodic chart, you have the atomic masses of the various elements. Now, that atomic mass is the mass of 1 mole of whatever element that is. So that 50.942 for vanadium is the mass of 6.022 times 10 to the 23 atoms of vanadium. Sometimes we say particles instead of atoms. So this image actually has samples of natural elements with their masses equal to their atomic masses, and each one of them contains 1 mole. So for example, this sample of copper at the top is weighing 63.55 grams. That's the atomic mass of copper, so therefore this represents 1 mole of copper, or 6.022 times 10 to the 23 atoms of copper. And the same is true for the rest of these elements. This represents 1 mole of iodine, aluminum, iron, mercury, and sulfur. They're listed in this table as well. And one thing I'd like to point out is that mercury, even though it has the same number of atoms in that image that you see at the right, weighs the most. So atoms of mercury are relatively heavy. So here's how we'll use moles. We're going to start by combining the molar masses of atoms. So the mass in grams of 1 mole of a compound, often known as the molar mass or the molecular weight or the molecular mass, is obtained by summing the masses of the component atoms of the compound. Here we're asked to calculate the molar mass of calcium carbonate. So what is the formula for calcium carbonate? Do you recall? Calcium carbonate is one of those polyatomic ions on the back of your periodic chart. And then we have to check the charges to make sure that they're put together right. Calcium has a +2 charge, carbonate is -2, so these can go together in a 1-to-1 ratio, calcium carbonate. Now, what's the molar mass? I'll look on my periodic chart and find that calcium weighs, and carbon weighs, and the 3 oxygens contained in the carbonate I put a little 3 here just to remind myself to multiply this number by 3 because it does contain 3 oxygens. Some students like to ask, do we need to use all of the numbers on our periodic charts? And the answer is yes. These numbers were obtained using measurement devices, so the shorter you cut these numbers, the more you're limiting the number of significant figures in any calculation you're doing, so you don't want to do that. Use all the digits. If I go ahead and sum these together, I find that the overall molar mass of calcium carbonate is 100.086. Is the central unit of chemistry. So if you know how many grams of calcium carbonate you have, and then you divide that number by the molar mass of calcium carbonate, you can find the number of moles of calcium carbonate. You can convert from moles to grams for any substance that's on the periodic chart. You can also convert from moles to particles and particles to moles, or moles to volume, which we'll do later in the year. Before I move on to the next slide, I just want to point out that the word particle is a generic term, but it includes things like atoms. So if you're asked to find the number of atoms, you're going to use this number, Avogadro's number, in order to convert from moles to atoms and back and forth. But particles can also include other things like ions, right? So those are atoms that have either gained or lost electrons and they now have a charge. Or particles could also include things like photons. When we learn more about packets of light energy called photons, we'll also be able to group those into the groupings known as the mole. So you can never convert from grams directly to particles. You can never convert from atoms directly to grams. The mole is the central unit. We have to convert from grams first to moles and to particles, or moving in the other direction. I like to remember that, and I usually write it at the top of my quiz. Here's some examples of how we'll be converting moles throughout the year and of course on our homework tonight. Calculate both the number of moles in the sample of cobalt containing this number of atoms and the mass. So I've been asked to find two things. The moles, I don't know that number yet, and the mass, I don't know that number yet. And the sample that I'm working with is pure cobalt. Okay, so here's my road map. I can convert from grams to moles to particles. And what have I been asked to find? Well, first of all, I've been asked to find moles. Do I have grams? No, but I have particles. So I'll start with the particle number. Remember, atoms and particles are used interchangeably. And then I'm going to use a conversion factor in order to convert away from atoms. And remember, the thing that I want to convert from goes in the denominator, and to moles. So what is the conversion factor between moles and atoms? Well, a mole is a grouping, so 1 mole contains Avogadro's number of atoms, 6.02, 6.022. You will have an equation sheet, so you'll know exactly which number to use. This set of calculations will yield the moles of carbonate. Start with 3 significant figures, end with 3 significant figures. And while technically this number is obtained using a measurement instrument and research, I do not want it to limit the number of significant figures, so I'm going to use at least 3 digits and maybe even 4, 6.022, depending on what my formula sheet tells me to do. So now I'll move on and convert the moles to grams. Again, how do I know to put grams in the numerator? I want to set my problem up so that moles will cancel. That means I need it in the numerator and the denominator so that I can cancel it, and grams is the unit that will remain. How many grams are in a mole? Where would I find that information? Well, remember, 1 mole of anything weighs its atomic mass. So if I check my periodic chart, cobalt weighs, and finally my gram number, I start with 3 significant figures, I end with 3 significant figures. This is something we'll be doing all year, and you'll practice for homework. I'm going to skip the second problem just for the sake of time. Feel free to practice it if you'd like. The next topic on tonight's homework is mass percent, also known as percent composition. So you know how to calculate a percent, right? To figure out what you get on a test, you put your part over the whole and multiply by 100. Per meaning out of, centa meaning 100. So what's your part out of the whole? Well, that's the same thing we'll do here. The contribution of each element to a compound is its molar mass. So if I take the mass of an element in 1 mole of a compound and put it over the whole mass of the compound and multiply it by 100, I'll find the percent of that compound that's made up of that one element. Let's do one together. Find the mass percent of each element in cobalt 2 phosphate. So cobalt phosphate, that's a polyatomic. Let's check the charges. The Roman numeral 2 lets me know this is cobalt plus 2, and when I check my periodic chart, I see that the polyatomic ion phosphate has a -3 charge. A plus 2 and a -3, so that means I'm going to need 3 of these for every 2 of those. That's cobalt 2 phosphate. Okay, so what mass percent of cobalt is contained in the whole cobalt 2 phosphate? I'll put the part that is cobalt. Now cobalt weighs, and there are 3 of them. Don't forget to multiply by the 3. Sometimes I like to write the little 3 here to remind myself so I don't forget. Then I'll put the mass of the whole cobalt 2 phosphate. So I have the part over the whole multiplied by 100. Notice that the units for grams will cancel, and the units for percent is what will remain. That's what I'm solving for, is mass percent. Now the limiting figure here would be the one with the least amount of significant figures. 100 is the definition of a percentage, so that can't limit us. However, a lot of times a teacher might ask you to report your percent as a whole number. Just don't be surprised if you see that, because we know it's out of 100 and it's just easy to round that way. I want to move on now to here's some more sample problems that you can try in class. I want to move on now to the last section before we start the homework. We've got 2 more slides. The last section is called stoichiometry, and that's referring to using the ratio of a balanced equation to make predictions about how much is needed or how much of something will be produced. Here is an equation that we need to balance. Now, we're not learning how to balance equations this year. You already know how from last year. It mostly takes patience and trial and error. Excuse me, those should be arrows. It has to be the same as the number that's here. If I have 12 hydrogens on the left, I need 12 hydrogens on the right. And I have 6 plus 4, that's 10 oxygens on the right, so I'll need 10 on the left. So once you realize how to balance the equation, now let's talk about why. What can we do with a balanced equation? Well, first of all, we balance equations to satisfy the law of conservation of matter, to show that no matter has been gained or lost throughout the equation. This represents a real world scenario in which 4 moles of ammonia reacts with 5 moles of oxygen to form 4 moles of nitrogen monoxide and 6 moles of water. Secondly, the mole ratio that we have here, 4 to 5 to 4 to 6, can be used to make calculations, and that is stoichiometry. If I know that I'm using 4 moles of this, I know I'll make 6 moles of that. What if I use 8 moles of this? Then I can make 12 moles of that. That's stoichiometry. Sometimes, however, these problems can get long and a little bit complex. And so we have this thing called the Stoichiometry Road Map. And the road map just shows us that if you know the mass of ammonia or one substance, you can convert it to moles, use the balanced equation, and figure out the moles of product, such as the water from our previous example, and then determine the mass of that water. So by putting all of our skills together, we can start out with a mass of one thing and determine the mass of another. Or start out with the particles of one thing, change to moles, find a different substance in the same balanced equation, and determine those particles. Let's give it a try. This is our same balanced equation from the previous slide, and here are some sample problems. Let's set them up and see how they should look. 3 molecules of oxygen react. How many grams of nitrogen monoxide are produced? This is going to have quite a few steps. I'm going from molecules of oxygen to grams of nitrogen monoxide. Now, what's a molecule? Is that the same as moles? No, molecules are particles, kind of like atoms, but O2 is not an atom. It's two atoms sharing electrons, so it's a molecule. Okay, so remember our roadmap? We can convert from grams to moles to atoms for particles, which in this case would refer to molecules. So if I'm starting with molecules, then I have to convert to moles. And then I can use the balanced equation to find the moles of nitrogen monoxide and eventually get to grams. If that seems like a lot of steps, you could use the railroad method. Remember, start by drawing a railroad track, given number, and write in what you have to find, and then work to determine what kind of conversions you need to use to get from the start to the finish. Okay, so if I want to change molecules of oxygen, those are particles. What's the only thing I can ever change particles to? Well, according to our roadmap, particles can be changed to moles. So moles of oxygen from molecules. That will cancel the units, molecules, and I'll be left with moles. Remember, once you get to moles, then you can switch to the species you were asked about, moles of nitrogen monoxide, using the balanced equation. And then finally, grams of nitrogen monoxide when you cancel moles. This is our plan. Let's go back over the units and see how they will cancel. Moles is in the numerator and denominator. Moles of nitrogen monoxide will also cancel, and I'll be left with the unit that I want. Now, what numbers should I plug in? Well, do I know how many moles of oxygen is in a molecule of oxygen? Right, a mole is a grouping, and that group contains how many particles? Exactly. Now, do I know the ratio of moles of nitrogen monoxide to moles of oxygen? Yes, from the balanced equation. There are 4 nitrogen monoxide for every 5 oxygen. So 4 of these for every 5 of these. Finally, do I know the ratio of grams of nitrogen monoxide to moles of nitrogen monoxide? Well, nitrogen monoxide has a molar mass, and 1 mole of it would weigh. All right, that's it. That's how I start with molecules of oxygen and end up with grams of nitrogen monoxide. Let's try one more together, and then you try the homework. If 34 grams of ammonia react, how many molecules of water are produced? So you can try the railroad method, or you can write the individual fractions. Either way, you'll start with the given number. I'm starting with two significant figures here. So if I plug the whole thing in my calculator, I should have two significant figures at the end. I forgot to say that this is three significant figures, so the final answer should have 3 grams of ammonia. So what would I multiply it by in order to try to get to molecules of water? Well, remember, always get to moles. Because moles is the unit that you can use to change to water from moles of ammonia. And then finally, you can go to molecules. Convert. Each time I'm setting up my proportionality so that the thing that I want to solve for is in the numerator and the thing that I want to cancel is in the denominator, and it's opposing the previous unit. Now I go back and determine what I can plug in. 1 mole of anything is equal to its atomic weight. So nitrogen weighs 14 and hydrogen is 1. That's essentially 17. Water, ammonia. From the balanced equation, the ratio is 6 to 4. And then finally, 1 mole of water contains, how many particles? Particles. So once I plug that in my calculator, I'll be done. Give that a try on the homework.